Hi, today on Make or Repair we're going to be doing a modification to this Agilent E4418B RF power meter so that it can adjust FET balance within the sensors that I'm repairing. It's part of a 4-part series. We're going to do a mod, we're going to do FET balancing, then we're going to do a build of a calibrator that we can then use to repair another machine. So let's get on with the modification to this meter. So this meter is calibrated, it's the one that I use day to day. The modification itself is actually detailed in Keysight's manual for the 8480 series power sensors. It's in an appendix to that, and I'll include a link down below and you'll see me following that later on. And the reason I want to do it is because of this power sensor. I picked this up second hand. On the face of it, it appears to work okay. It's missing an attenuator for calibration purposes, but that's no big deal. What I did notice, however, is that on the back of this there is a series of screws and there's a connector, and the back's obviously been taken off. Now if that's happened, then there's every probability that the FET is no longer in balance because it is heavily affected by the cabling between the board and the connector. Hence I want to make a device so I can measure that. So this is a generic diagram of a power sensor, and it doesn't really matter what type it is. This is the HP design, and all of the 8480 series is the same as this. It'll either have on the front end a thermocouple or a diode, depending how sensitive it has to be. So let's run through. So we've got the input coming in. This is our RF source over this side. Now what I need to do is perhaps just have something so I can draw something here. So yeah, input just here. Okay. So this goes through into the thermocouple or diode, and it just has a resistor beforehand just to give it the correct impedance, which will be 50 ohms typically. Okay, so the thermocouple or diode translates this into a really small voltage. So we're talking nanovolts or microvolts at this point. Now it's important to note that this thermocouple diode sort of sensor package on the front end is incredibly sensitive. It's sensitive to noise. It will be well packaged. You probably have to replace it as a whole piece. Not very repairable. It is not grounded, so it has two outputs which are essentially floating, and there's a little bit of capacitance here, which is sort of grounding. It's providing a ground reference for the chopper. So what the chopper is going to do essentially is really kind of connect these opposite sides of that pair against ground to produce an AC signal. So the output from the thermocouple diode is DC, ridiculously small signal. The chopper is going to take the top end and the bottom end of that against ground and output that as an AC signal. So we've got chop inputs. Let's write some letters here. We've got chop inputs just here, which are alternatively switching these two switches. Now these switches are FETs. That AC signal goes through this capacitor and into what I've shown as half an amplifier, and that's because there's a transistor in the power sensor which forms half of an operational amplifier, the other half being in the front end of the actual meter itself. So this is why they're all kind of the same and they're paired up, because the meter and the sensor share an amplifier between the pair. Part of that is because the meter needs to give feedback to the sensor so that it can calibrate it, it can set the 0 point and things like that. So to set the 0 point, the meter can output 0 volts on this line and into the input of the amplifier, essentially getting rid of whatever is coming through this capacitor to a large degree. It will also zero the input. So that's its zeroing mechanism. So it's zeroing the amplifier error out of the circuit. What we also have down here is feedback within the amplifier loop, and that is going through a thermistor, which is reducing the temperature drift of the whole device. Now, what can go wrong with this? Well, there's two issues that occur calibration wise. So these two switches in the balance chopper are FETs. Now, it kind of gives it away, balanced chopper. So these FETs are not going to be in perfect balance. They're going to have, manufacturing differences. There's going to be slightly different capacitance. What's not obvious on this diagram is that a lot of these things here are actually wires. These are wires going from the FET all the way back to the connector. They have capacitance, they have inductance, and that's going to affect the switching and balance of these two FETs. So if we put 0 volts in, we should get 0 volt differential between the two lines going into the chopper, and we should get a flat DC 0 volt coming out of it. That is not going to happen. The chopper will add a positive offset on one side and a negative offset on the other side, just by a very small amount, and we need to minimize that because that is an error term going into the amplifier. Now, if we've got a huge input, that error term is going to be very, very small and won't make a big difference. If, however, we've got minus 70 dBs going into this diode, then the output is in nanovolts, and that could actually be swamped by the error term on the chopper. And you can only zero that out in software and things like that down the line to a certain extent. And this is why often you'll get a sensor, you'll plug it in and it works great at the high end. So for example, I've got a minus 70 to minus 20. It works fantastically at minus 20 dB. It's fine at minus 50. And it starts getting very accurate at minus 60. And minus 70, it's unusable. And that's almost certainly because of offset and noise in this chopper. The other problem that occurs with this, FETs, when they switch, we can actually get a spike. And I'll draw up a quick diagram so we can see that. I'll pop this out of the HP manual that I was referring to, where it talks about how to do the balancing. So this is out the sensor service manual, and this is showing an unacceptable output. So we can see some characteristics on here. Let's try and get this. It's nice. So just here we can see spikes. There's another one just here going down in that instance, and another one just here. So this is a clean downward spike. This one's got some up and down in it, and we will see that when we actually come to do the work on the sensors themselves. The other thing that we can clearly see is the offset in voltages that's going on here. Let's get rid of some of these. So this is set to this scope is set to 50 millivolts per division. So you can see that this is more like 7. Well, how much is difference between those? Hard to tell, but certainly more than 50 millivolts difference between those two levels. If I say that one's there and that one's about there, then that's 75, 80 millivolt difference, and you can see the amount of noise that's on here because of the amount of amplification. So to get that trace, we need to take the output from these amplifiers. It goes through yet another amplifier, and we eventually get to a high gain block in the meter, and that's where we can take out the calibrated trace that we're interested in order to find out how out of balance these two switches are. To repair it, generally speaking, what we have to do is move these two wires around to actually, and then those levels and these peaks will actually adjust. Okay, so we're ready to go. Got the anti-static mat out. Here's the meter disconnected, and all the grounding precautions. And the first job, of course, is to open up the case. This is a T15 Torx that I'm using, and I think there's only 2 screws and the handles that hold this case together. So we'll just pop that, try and pop that off. Okay, a little bit more stubborn than I expected. Okay, and that's the whole back section removed, and we can see that the case is really just a sleeve over the inside. Next job is to pop the handles off. You do now just pull the handle out. Unfortunately, I missed a page, so I wasn't aware that you have to turn the handle to a specific angle in order to do so. I got there in the end, though. There we go. So do find that manual page so you don't damage your handles, and then the case just slips off, and we get our first view of the inside. Slightly dustier than I might like. When I've finished, I'll take this outside and I think just give it a quick spray with some air. A little bit easier. I've taken a still from the video. So this is the top board that's already visible. You don't need to disassemble the meter anymore, and we're going to connect 3 wires to this, and they're just straightforward pieces of wire going to a BNC. They're not screened or anything like that. Anyway, where do these wires go? So the first one goes here, next to the label U8 chop, and this is the chopper output, and it's going to be the trigger for our oscilloscope. Don't take the end chop, a little bit higher just there. I'm not quite sure what that signal is, but I double checked in the manual, and it's definitely the one labelled U8 chop that you want. I suspect the other is just the inverted value of that, but the next one we need is here on the left hand side, and this is the high gain output. This will be used as the trace on the oscilloscope, and it's the maximum amplification of the signal coming out of the sensor. So exactly what we need to see the magnitude of difference in the balance of those FETs. Next to it is the low gain output, so just an earlier stage of amplification. I'm not 100% sure why we particularly need that one. It's in the modification though, so I decided to install it. And that's a lot. These are already plated through. They can be soldered from the top side, so everything's pretty good. Okay, switching to look at the back of the LCD. Just taking a quick look at this because I intend to replace this. I don't like the orange low contrast front panel, but I'll have to make up a board. I'll do it as a separate project. Looking at the back panel, we can see some holes here for BNC connectors. They're just on the back of the plastic. I have to cut through with a scalpel. And there's already a plug on the back as well for the third BNC connector that's needed. So just a bit of simple scalpel work, and there's already a hole through the bulkhead for me to feed my cables. So other than being slightly awkward, that should be no problem. So just going to prepare the back panel. First of all, take the little plug out. It's a little bit awkward with the screwdriver. Just can't get it out that last bit. I'm going to switch to a pair of pliers. These are just thin pliers. Out it pops. And now I need to actually cut through the back panel with a scalpel. It's not too thick, it's slightly flexible. I can find the hole, and I'm just using the sides of the aluminium to guide the knife to get a really clean, neat cut. And just repeat for the second one. Okay, so just cutting around using the aluminium. Probably have to throw the scalpel blade away after this, but there we go, all done. Okay, here are the BNCs I'm using. They're recycled. They have the screw fastening on the back, so that everything stays neat. And all we're going to do to prepare them really is attach a length of wire to each one, probably about 300mm a foot long. The manual says to fit AWG20 wire, but I probably haven't got anything quite that thin. I'll just make do with something just a tiny bit thicker. Okay, so we start off, we're just going to trim this wire. So I've trimmed that to, I don't know, 5-6mm, something along those lines. First we'll put a tiny bit of solder on the tip, apply that, and just make sure that the soldering center is properly melted. Freshen that up a little bit. I'm then going to apply a small amount of solder to the wire that I'm fixing. Spin this round, and this is a half cup receptacle on here, so it sort of sits into it a bit there and then slides in, and that's your lot. Easy peasy. So just a couple of these to do. Okay, so here they are, all three of them. And I've added a little bit of heat shrink on there as well. It's not strictly necessary in this particular purpose, but yeah, quite good. I did toy with switching to a coaxial cable so they could be screened from here down, but the spec doesn't say that, and there's already some similar joined up connectors in the back that don't use coax. So I'm going to just do what it says in the manual. Bit unusual for me. So I'm not 100% sure how I'm going to do this without getting my fingers in the way of the camera. I'll do my best, and I'm going to start with the most awkward one, which is underneath the existing recorder location. I can take that out, I think, if I need to. It goes into a plug socket on the circuit board, but I prefer not to. So I'll just thread this cable and the item, and that fits nicely and even matches the existing one. And then on this end I'm just going to thread the lock nut and the nut, and try and get the pair of them, oh dear me, to go cleanly onto the nut. I've managed to get the lock nut on, the lock washer rather. Yep, there we go. Whew. Now it does specify a wrench size to use on this, but I can't really see that. I'm going to have to get in there. Okay, they're the right ones for that, but this one actually has a slightly smaller fitting. Gosh, these are very difficult to get out. Okay. So I wouldn't recommend using thin pliers like this for tightening nuts. Particularly if you've got to do so without putting your hand in the way of a camera. So I'm just using these to edge the nut around a little bit so that I can actually get the end of the spanner on it. And I'm going to use this offset end. It has more locations. Okay, I think we are there. Lovely. And this needs to feed through somewhere, and that is what this gap in the bulkhead is for. I'll show you that in a second. Whew, two to go. These have got slightly larger nuts on. I can swap them out for something smaller if needs be. And we're in. They're all nice and firm. They're well connected to the back. And now I'm just going to choose which one of these is going to go to which hole on the circuit, because obviously I'm going to need to label up this back panel. So I'm just choosing which connectors are going to have which function. So I'm going to put high gain at the top, low gain at the bottom, and then on the left hand side will be the chopper. And I'm just going to mark them up onto my notes so that I don't slip up later on when I'm joining them up. Okay, so I'm just going to position each wire next to its hole, chop it off, leaving just a little bit of excess, and paying attention to keeping the wires neat and tidy. When they're all together. Just don't want wires hanging around all over the place. So you can kind of see me grouping the wires. Unfortunately my hand's a little bit in the way, but I think you get the idea. Group the wires together, look how they'll route, cut them to length, and then we're going to strip the ends, tin them, and solder them. And yeah, I use these old-fashioned strippers. Okay, so just tinning the ends. I'm not putting much on these because these wires are actually quite thick. They only just go through the hole in the board. Ideally I should have used a slightly thinner cable, but I haven't got any in stock, so we deal with it as best we can. Okay, gently inserting the wires for soldering. I just lift this out of the way a little bit so that I've got enough room to get the soldering iron in there. Unfortunately, I did manage to get my hands in the way of the video, so our video doing the blue one. So they're just standing proud by about 1 millimetre or so from the board, and I cut them quite short so they don't stick through a long way on the back side. And I just apply a small amount of tinning to the tip of the iron. Bring it in on the junction between the pad and the wire, and then introduce the solder gently in from the opposite side. Hold the iron on a little bit and remove, and it's done. And that solder would have flowed right through the hole and soldered fully on both sides. So just got to connect the last one now. Okay, so here are the connections. You can see the high gain on this side, low gain on this side. Coming back here, this is our chopper, which is going to be our trigger. And they went quite neatly through. I'm just going to put a little tie, perhaps just a couple of light cable ties in there, just to hold it all together. Okay, I've done a quick blowout with some air to remove all the junk from there. These parts looked a bit dusty, but not too bad, but the power supply was absolutely caked. And now I'm just using a bit of isopropyl alcohol with some water, so it's around about a 70 to 80% isopropyl alcohol, just to do a little bit of cleaning just before putting it all back together again. You know, so it's a lot easier while it's in pieces to get at things like the edges of these rubber bumpers and things. So far, so good. So I think while this is in this position, I'm going to just clean and replace the back bumper. And then I'll do the same with the handle. Yep, that's that. And we just need a Torx 15, if I can find it. So that's not bad really. I mean, yeah, 2 screws, not all that's required. Okay, it has a clip. This is probably why I had difficulty getting it out. So on this side, this hole is not round, it has a little point on it, which is like a little key on it, and there's a corresponding key on here, so you need to fit that way up. Oh, that gets so much easier when you know. Okay, and now it locks into its various positions correctly. Lovely. So that's that side done. Now I just need to turn this around and label up their back. Just pop that on a wheel of wire just to hold it in place while I'm doing that. There's not a lot of space in there. And low gain. Not the neatest. I would perhaps have been sensible to have fixed this before putting this on. But it can always pop off again. Give me a bit more room to play with. Oh look, so much better. Ah. Unfortunately, low gain covers up the earth symbol, but I think we probably know what that is. These stickers that I'm using are crazily sticky. Right. I'm not sure that really helped all that much, but yeah, it helped a little. That's great. Modification finished. Let's just turn it on, make sure it works. Power meters themselves aren't too expensive, particularly if you go for an older model than this. So this is a reliable calibrated 8482A power sensor. Which, I can't remember what it goes to. So mine is 30 plus 20 dB, I think. Something like that. Let me just move things around a little bit. And as you can see, brightness and contrast does leave something to be desired. Okay, so that looks absolutely fine. To calibrate this fully, I would need to warm this up for about half an hour. And then I do this, press 0 cal. There's the cable, just under here, there's a button called 0 cal. And then I press 0. And it will spend a bit of time zeroing that. Or nearly zeroing that. And then we press cal. Okay, and there we have it. 0 dBm, which is exactly what you expect to be coming out of the power reference. So jolly good. You do have to set, just here there is a reference factor, which for this is 99%. It's printed on it. So you have to set that when you calibrate it, so it knows how to make adjustments for it. For the newer sensors, this does have this has an EPROM in it, and with all the calibration factors for all the different frequencies, and this will read them in and use them. So as a quick tease for the next video, here it is all connected to the scope, and we can see here the offsets and spikes that occur for, this is an 8484A sensor, and it's slightly out of spec but not hugely. So yeah, so we can clearly see the chopping effect and the two offsets that are coming out the FETs. But more of that in the next video in the series. If you enjoyed this, please thumbs up, like it, subscribe, and of course you can always leave comments below. Thanks so much, take care.